Good morning, everyone. My name is Dr. Subhasis Das. I am working as an associate professor in the Department of Electronics and Communication Engineering, SR University, Warangal, India. Today, we will discuss about some basics of different types of diodes, and we will try to figure out the working principle and what is their applications and how we can explain the different types of diodes quantitatively and qualitatively. So today we will focus mainly two types of diodes, namely the Varactor diode and the tunnel diode. We will go one by one. Okay, so we will see what is Varactor diode and their working principle and what are some applications of Varactor diode, and then we will discuss the same things about tunnel diode, their working, the IV characteristics, and the application at the last. Okay, okay, let's start first the Varactor diode. Okay, so as the name suggests, the Varactor diode, also known as a varicap or gold cap, and it is a type of PN junction diode primarily utilized in the reverse biased mode. Okay, so for the basic understanding, we can simply think that character is equal to variable reactor. Okay, here reactor basically means the device which has electrical reactance, right? So which kind of devices has this thing? Basically, we know inductor and capacitor has this property, right? So that means it will basically working as a variable capacitor, okay, or variable reactor in that sense. So the short form becomes Varactor diode. Okay, why diode? Because this is the actual function or the working principle is diode, but essentially as per the output function is concerned, we will see that it is following the uh, reactance or the capacitance rules. So, as we have already discussed, utilized for reverse biased mode. Okay, so we will see how we can do that. So this is the basic definitions or understanding of Varactor diode. Right. So this is nothing but the PN junction diode, but we design this specially for a particular purpose of reverse bias mode. Okay, so this Varactor diode is typically made from semiconductor materials like silicon, gallium arsenide, and germanium, like all these things. So this does not need to be mentioned, but still, for your better understanding, we just mentioning some of the name of the semiconductors from where this type of diodes are made. Okay, and here is the image for this diode, right? So the basic difference is that here you can see that capacitor symbol is there, right? So that means this is diode, but it has this capacitance effect. We will see next. Okay. So this Varactor diode is designed with a specific focus on its capacitance properties and its ability to store charges. Okay, so as you know that the parallel plate capacitance formula will be used. Okay, generally we know the parallel plate capacitance C is equal to epsilon A by D. Here epsilon is the permittivity of the material, A is the area, and D is the depth or thickness, like that. Okay, okay, we will see this formula now. Okay, this is the general formula. So the Varactor diodes have capacitance varies with changes in the applied reverse voltage. How this is happening? We will try to see this thing now. Okay, so from our understanding of the PN junction diode, what we can see here is that as we change the reverse bias applied to it, the width of the depletion layer also changes, right? How? We can see from this image, so this is the width of the depletion layer, right? So this is the width of the depletion layer, and now here in this image it is showing that we are applying a reverse bias because this positive terminal is connected to the n type, right? So from positive here to the n type, and p type is connected to the negative terminal, right? That means this is reverse bias. So this has been extended. The depletion region has been extended due to this reverse bias. Okay. And when this extends, because this depletion region is actually works like a parallel plate capacitor. So that we changes means as per the formula we understand that the capacitance also changes. Okay. So let's read this line again. The Varactor diode's capacitance varies with changes in the applied reverse voltage. Okay, that means the applied reverse voltage, if it increases, the varies with depletion width. As we change the reverse, so varies with depletion width. Depletion width. Okay, so as we increase the reverse bias voltage, the depletion width also increases. But as per the formula, if you see the formula, this width comes at the denominator. That means when the width increases, capacitance decreases. So if we try to see the relation between the capacitance, then we can see that this capacitance actually inversely proportional to the increase of, so this capacitance varies 1 by the reverse bias, because when the reverse bias increases, it actually increases the depletion layer width, and when the depletion layer width increases, it actually decreases the capacitance, because as per the formula Ct is equal to epsilon A by W. When the W increases, the Ct value actually decreases. So finally we will see that the capacitance Ct varies as the like inversely proportional to the reverse bias. Okay. So here CT stands for transition capacitance. That means basically there is change of capacitance due to the reverse bias, and as you know epsilon stands for the dielectric constant of that particular region. Let's say this region, So this is the depletion width, right? So this is depletion width region. So this region is depletion width region. Okay. So this is the depletion width, right? So this is depletion width. We can easily see that the dielectric constant at this region is denoted by the epsilon. Okay. And A, of course, here stands for the capacitor's plate area and W the depletion layer as we are talking. Okay. So this is how we can see the capacitor varies with the reverse bias applied at the PN junction. Okay. So where it is used, now we will try to see some application of Varactor diode, because in every innovation or every kind of new devices we need a solid motivation, and the motivation is actually the application. If there is some application which requires this type of device, then only it is worth discussing about that device. Okay, let's see something like that. Okay, that is the application of tuning circuit. Okay, so here is the circuit. We can see, so this is the circuit, right? And here we can see in a tuning circuit, the Varactor diode is, so the Varactor diode is connected in parallel with a fixed capacitor. Okay, you see here, this is D1, this is D2, right? Often in an LC, inductor capacitor resonant circuit, right? So let's try to understand the circuit configuration. Here one resistance is connected, here diode, and here diode. Okay, and it is mentioned that the Varactor diode is connected in parallel with a fixed capacitor, right? And in this symbol both are showing as the capacitor. Okay, so the CT here, the CT is Ck divided by Vb minus V whole to the power m, right? Where V is the applied voltage. You can see here the applied voltage, and C stands for the diode capacitance when the device is unbiased. Okay, so for your understanding, when there is no bias applied to the diode, still it carries some capacitance because of certain depletion width. Okay, if you bias like reverse bias or forward bias, then the width changes, but it is not like that without the bias there is no width, right? So that means without the bias there is also certain width of the depletion region, and because of that we can notice some sort of capacitance without the biasing. Okay. And Vb stands for the barrier voltage at the junction. We know the uh, potential barrier at the junction of the PN junction diode. Okay, here M stands for the constant depending upon the material. Okay, because if the material changes, some constants on the material parameters also changes, and that will be considered into M. Okay, now we can see that the curve of this Varactor diode. Okay, here you can basically see the CV curve, right? And it is showing exponential increase. Okay, why it is in the left hand side, like because of this reverse bias, we are starting from 0, we are considering this is 0. So because to understand that thing, we are showing at the left hand side to better understand about the reverse bias. Okay, so As we have already discussed that when the reverse bias increases, actually C decreases, and the same trend is showing here also, but the nature is not linear, it is exponential in nature. Okay, okay, let's try to analyze the characteristics curve. Okay, it shows the nonlinear relationship between the capacitance and the voltage applied. Although we are directly saying that it is proportional to this thing, but it is nonlinear in nature. Okay, the width of the depletion region increases with the reverse voltage. The capacitance decreases, that is varies inversely as shown in the graph. These things we have already discussed in our previous slide, and it is also just reiterating the same thing, right? So if you see here, you can easily understand, as we are going in this direction, right? We are going in this direction we are going, and our capacitance is decreasing as per this thing. And finally, at a certain point, as it go on increasing, it seems like capacitance is reduced so much that it looks like that it has saturated. Okay, in short, as the reverse voltage increases, the transition capacitance falls rapidly. It falls rapidly, and after certain time, let's say after this, it becomes to be saturated and looks like that capacitance has been already reduced very deeply. Okay, now we will see some applications, or basically just try to understand why do we need to learn this thing at all. Okay, for this case, we'll see some applications like tuning circuits. Okay, you might have noticed some circuits you just from the outside, let's say some amplifier or some tuning circuits where the fine tune is required. So in that case, your Varactor is already inside, and from the outside you are just rotating some knob. Okay, just to vary the capacitance actually. Okay, so here is the big use of this kind of Varactor diodes, right? The frequency modulation and voltage controlled oscillators, or VCOs. Okay, so these are few applications where this kind of reactor diodes are very much useful, right? Okay, so far I think everyone already understood the usage of reactor diode and how this operates. This is very much simple. The only thing is the reverse bias is increasing in the diode, depletion region is increasing, and as a result the capacitance is decreasing. That's it. It is as simple as that. Okay, so now we will move forward to another type of diode, which is called the tunnel diode. Okay, so tunnel diode, this name comes from its uh, working principle, the way of operation, but initially it was named after its inventor, that is Isaki. So Professor Isaki first invented this kind of diode where the mechanism of quantum mechanical tunneling is applied, and it was first named after him, that is Isaki diode, but sometimes, or more popularly known as the tunnel diode, because of this tunneling mechanism is the main working principle of this kind of diodes. Okay. In the normal diode, generally what happens, the electron from the n-side conduction band wants to jump through the potential barrier at the junction, and obviously opposite same thing for the hole and the p side. Okay, but for this case, what we will do, that we will make our diode such a way that our depletion region width is so small, so that the quantum mechanical tunneling phenomena will take place, and as a result the electrons or the holes does not need to jump jump over the barrier. they can just tunnel through it and reach to the other side. And that will make our job very easy, and we will see a huge application of this kind of diodes. Okay, so let's start now. So it is very heavily doped p-n junction diode. I just told you the same thing right now, that if we consider this is a p-n junction diode, this is p side and this is n side. So these things we are making the junction very thin. Okay, maybe the earlier junction were like this, and when we make this p plus and this side n plus, the junction shrinks to this. Okay, understood? Okay, so better understanding will make this thing. Okay, so earlier it was like this, where it was p and it was n. So now after heavily doping both the sides, we can see that okay, after heavy doping we can see that it becomes the depletion width region becomes so thin that the quantum mechanical tunneling is possible now. Okay, so that is our one of the motivation to have a heavily doped p-n junction. Okay, the electric current decreases as the applied voltage increases and at high voltage. Okay, the electric current decreases as the applied voltage increases and at high voltage, right? The tunnel diode electric current is due to the tunneling effect. Okay, so the circuit symbol of the tunnel diode is like this. If these two portions are not there, it is similar to the normal p-n junction diode. But because to represent the tunneling effect, we are putting these two things here and here. Right. So this is the circuit symbol for tunnel diode. Okay. Working principle, as I explained in the earlier slide also, the width of the depletion region is very thin. Okay, so we know this thing theoretically, that if the depletion region is very thin, then the electrons from this side can tunnel through the other side. And same thing for the holes also. Holes from the other side will tunnel through this barrier and reach to the other side. Okay, so this makes us uh, wondering how we can do that. Okay, here is the solution then, that if we keep on increasing, let's say initially the depletion region was like this, but if we start doping the materials from both sides, p type and n type both sides, then the depletion will start shrinking as the donor level or the acceptor level is increasing. Okay, here we can make it asymmetric also, but ideally we will go for the symmetric doping for the both sides, so that the depletion region shrinks from both the sides. Okay, and when the uh, sufficient doping is completed, we will see that it shrinks so much so that quantum mechanical tunneling conditions are satisfied, because for that your uh, the barrier width should be very much thin, and when this high doping is taking place, and this makes our barrier very thin, so that this tunneling conditions are satisfied. Okay, now if the concentration of impurity atoms is greatly increased to a level of 1 part in 10 to the power 3, the device characteristics are completely changed. Okay, so this we will see in our next slide that when that concentration of impurity atom means basically the dopants. Here impurity means the dopant atoms or the dopant molecules, okay, which is working as the donor of electron or the holes, okay, for both the n type and p type sites. Okay, so this is clear, right? We'll go for the next slide. Okay, now we will see the VI characteristics of tunnel diode. So VI means voltage versus current characteristics of tunnel diode, right? So this is very interesting because as you can see in the right hand side image, the current first increases. Okay, so this thing, the current first increases as the voltage increases. You can see here. Okay, I'll change the color. Okay, for better understanding, I'll make this. So this current is increasing up to this. Okay, up to this it is increasing, and after that, what happens? That if you increase the voltage from here, this is called the peak voltage, right? This is called the peak voltage, and after that if you keep on increasing the voltage, the current is still decreasing. Current is actually decreasing. But okay, we will not go into the details of the band diagram. Then we would see that actually this decrease is not absolute decrease, because if you see that we started from here but it decreased up to a certain level, which is called the valley point, right? So up to the valley point, this current is decreasing, and at this voltage, the voltage is called the valley voltage. Earlier the voltage was called the peak voltage, and this voltage is called the valley voltage, okay, VP. Earlier it was VP. So and after that the normal conduction method starts. Normal conduction method means the regular p-n junction characteristics of forward bias, which is the typical nature of the p-n junction, that is the exponential increase. So after the valley point, it actually starts or behaves like a normal diode, which shows the exponential increase of current with respect to voltage. Okay. So in the first phase, the current is dominated by the tunneling current. Okay, initially the current is dominated by the tunneling current. That's why as soon as we apply some voltage, the current starts increasing very rapidly and immediately. Okay, and after reaching certain point, when the both side bands or the both side the Fermi level or the electronic levels are matched, then it reaches to its peak. Okay, and after that it starts decreasing. And here is very important region. We can divide this into three different regions. Okay, so first region we can call this as the tunneling current region, and the last region after the valley point, because it is working like a normal or the conventional diode, we can name after this the conventional diode region. But the middle region is very interesting. Okay, middle region is called the negative resistance. Okay, here comes the concept of negative resistance. Why? We generally see the resistance is always positive. Okay, then how is it possible that resistance could be negative? That means here negative symbolizes that the current and voltage change directions are not similar, but they are opposite. Because here you see that voltage is increasing, right? The voltage is increasing but the current is decreasing. That means if you want to see the value of R, which is, let's say, delta V by delta I, Okay, if we make it delta R, so delta, so that will become delta V by minus delta I, because if the delta is increasing, delta I is decreasing, and finally it becomes a negative term, right? So it becomes a negative term. Okay, that's why the name came as the negative resistance region. Okay, so this is the main or the basic interesting thing about the tunnel diode, that it has a negative resistance region, it has a tunneling current dominated region, and it has a conventional diode region. So these three regions of operations are mostly important for any kind of analysis of tunnel diode. Okay. Now we will see some applications like microwave applications where this negative region is very much important. Relaxation oscillator circuit, logic memory storage devices, frequency modulation receivers. So all these are different types of applications where this type of tunnel diodes are being used. Okay. So what are the key summaries from this lecture? So from this lecture, what we understand that Varactor diode capacitance changes based on the applied reverse bias voltage, and in the tunnel diode, forward current rises sharply as the applied voltage is increased initially because of the tu- tunneling dominated current. Okay. So here I hope you have learned about these two types of diodes. So the possible questions from here are the describe the Varactor diode with working mechanism, and the second one also similar from the tunnel diode. Okay, and also to explain the PI characteristics, which is mostly the important one, rather explaining the tunnel diode. Actually, both are related. If you can explain the physical mechanism of the tunnel diode, then you will be very much be able to explain the VI characteristics. Okay. Okay, that's it for this lecture. We will see you in the next lecture, which will be some topic from the device side. Okay. Thank you everyone for watching this video.